Record. Okay. So, I didn't record the past minute, but I am just going to repeat the important parts so that it's clear from the beginning how things are done. Electrostatic fields are solved 100% of the times using potentials because it reduces the dimension from 3D, 2D. It reduces always to a 1D problem. So because of that, we use potentials. And the reason why we use potentials, so we can use potentials, is because the curl of the electric field intensity is 0. And there is this relationship that the curl of a field that comes from a potential is always 0. Therefore, I can define, then I can put these two equations together because they look the same, and I can define a definition that the electric field is the gradient of the voltage. And to give it the physical meaning that we understand, we put the negative sign. The physical meaning is that the electric field is the force from bringing a charge from the infinity to a certain point against the force of the field. So for that reason, we put the negative sign in there. And then we substitute this thing into there. Well, first into here. First, we put it here into here, and then we put it into here. So we get, I am going to use nabla, even though I don't like it, but I have a mixture of equations here, so I'm going to use the divergence of D. So D would be the divergence of epsilon E. All right. And it was to the density, charge density. And then I'm going to change E. I'm going to change E there. So this will give me the divergence of epsilon negative gradient of V equals to rho V. All right. And that would be the equation to be solved. And that equation is, if you go into console, you will see this equation, right? For fields, for epsilon, for permittivity, if epsilon is constant, then we will have that the divergence of the gradient of V is equals to rho V negative. Therefore, the Laplacian over epsilon, the Laplacian of V equals to the negative of rho V by E. Okay. This equation has the name, a Poisson equation. Poisson equation when rho V is equals to 0, then it changes to the Laplace equation. Okay, and this is the Laplace equation. It has name. The names are meaningless. All of the methods we're going to use are applied equally, regardless of the name. It has the name of the person who worked on it. So in the solution that to this equation was obtained by Laplace. That's why the equation carries his name. So because Laplace solved it analytically for certain things like this square. Laplace had a square where the potential is distributed like that. So that was the sine and cosine together with sine and cosine hyperbolics. But this is not a class on a analytical solution. So I stopped there, and I wanted to get the Coulomb gauge, and so the Coulomb gauge is really is easy to obtain. I don't know why I didn't remember at that time, but then I just checked, and it's it's easy to get, right. Um, the Coulomb gauge is obtained from where? No, that has to that this is not for this. This is not for this. I'll do it for the electron. So forget about this. I thought I was gonna go that. All right. So now I am going to go through the solution methods. Solution methods for that equation. And I'm gonna put here, instead of putting this, I am gonna put here later the magnetostatic or the DC current, and then it will be fine. And let me take it out of the way. Okay, solution methods. How do we solve these things? So as you can see here, we have only one equation. We have a single equation here. And to compute the electric field, because the objective is not to compute the voltage, to compute the electric field, we are simply going to use the gradient of V. So what we need is to solve this equation. All right. How do we solve this equation or that equation? It doesn't matter which one of them we pick. Of course, the Poisson equation has a little more complication, but it's like a differential equation that is homogeneous or non-homogeneous. That's all it is, right? If you were to develop this equation, it will be the second derivative with respect to x second of voltage, which could be a function of x, y, and z. And it will have the second derivative with respect to y2 of v, x, y, and z, plus the second derivative with respect to z of voltage x, y, and z, and it will be equal to 0. So that's the homogeneous. And if it is the non-homogeneous, it will be equals to minus rho v by e, right? So how do we solve that equation? Well, it's a partial differential equation on a 3 variables. And there are methods to do it for geometry. And normally, so this is the equation that we solve, and normally it's subject to boundary conditions. And the boundary conditions are equivalent to the initial conditions just for space. So boundary conditions refers to space. Because this is not a variable in time equation, then the equation is only in space, so it will have to be limited in space. The typical thing, the mostly talked about problem, is a conductor that has a voltage applied, and that is the typical example in every book that you can find, right? So it has a voltage applied here and grounded. So it's two conductors, one with a voltage applied and the other with a voltage grounded. And this is the problem that Laplace solved. And the solution, voltage of x, y, and z, there is not going to be only two dimensions. It's something that has hyperbolic signs and sines or cosines, depending on how you solve it and how you go. And those things describe things like that. All right. But we're not going to go that way. This is a beautiful thing for a course when you want to solve some problems analytically, but we're not going to go that way here. Now, solution methods. I am going to describe them all. I'm going to go with their advantages and disadvantages, and basically say that all of them had advantages and disadvantages, but the only one that can do all the solutions is a finite element. But it's not always the most adequate. It may not be the best method for certain things, but it's the only method that can do everything. But it cannot necessarily do it more efficient than other things. Closed forms. So the closed form solution has a, it's basically go and integrate this equation, right? Go on and integrate this equation and get the solution, and can only work well. Can only work well. Let me see if I have closed form solutions. All right, so I'm going to describe them in here. So these are the all the methods that I know. There may be more. Closed form solutions. These are actually very good. It will give you insight. So, but it's only for I wouldn't say regular geometries. It only works for cubes, cylinders, and spheres. That's it. Now, um, for an electrostatic problem like the one I put here, it doesn't matter too much because we are going to solve it by potentials anyways. But um, transforms, transforms like Fourier transform, Laplace transform, and many other transforms that exist. What they do is they reduce the dimension by one. Imagine what you have when you may have eventually a voltage that is a function of x and time. When you use a transform, your voltage is going to be a function of x and s, the function of the Laplace transform, the Fourier transform, if you wish, Laplace or Fourier transform, it doesn't matter. And therefore, all the s elements are taken in algebraic. So reduce the dimension by one of the reduce the dimension of the differential equation by one. Now, numerically, the one that is, I would say, easiest for somebody to build. Let's say that you don't have access to finite elements program, but you still have a complicated problem that you need to solve. Finite differences is something that you can do in a MATLAB code if you wish. It's relatively easy. And it can deal with many things. It can deal with nonlinearities. It's actually a great way, and it's easy for people to do things that are easy. It has problems. The problems are related to the need to have a CAD program. So you need to attach it to a CAD program if you want to solve generic problems. But you can tailor it to your particular problem, and you can make it even more efficient than final element. Now, final elements is the object of this class because is a general method that applies to whatever, and it has no restrictions. So for me, of course, this is the best generic. So it can solve almost every problem. Now, a integral equations. Integral equations is a beauty. It's a you can solve things very efficiently. For example, if you had a problem related to insulators in an substation or insulators in a transmission line or something, I would say go directly to an integral equation, and there should be programs already available in the market that solve the integral equation of an insulator change. So provided that you keep your problem linear or your problem is linear, integral equations may be very efficient. The matrices that we need to solve for finite differences on finite elements are very large and sparse. And the equations that you need to solve for integral equations are dense, but they are very small or relatively small in comparison. And there are other methods that I call them physical, in which you do, for example, charge simulation. So that's the typical to do charge simulation, or there are other things. You can have current filaments, and you can do a lot of little things with physical understanding. But again, you need to do a lot of the work because there are no commercial programs on that. Okay, so let's go one by one on the advantages of the different things. So, honestly, the closed form solution is the one I like the most for an introductory class to electromagnetics. But if you want to solve a problem, it's going to eventually get you into trouble, and it's going to have solutions that you don't want to get into them because may not be easy to obtain or to explain. But the advantages is that closed form solution give or gives a closed form solution gives deep deep physical insight. So if you want to understand how things work, take the advantages. So if you have a problem that has this ugly shape, let's say it's a conductor that you have formed into this way, right? For whatever reason. I mean, you probably need it for something. So if you can, or I would even say, try to get a cylinder in there and solve the problem analytically for the cylinder. The good thing is that the problems are already solved. If you get the book by Smythe, I think it's a 1948 book. It's very old. 1948 from Smythe. That Smythe has analytical solutions for hundreds of different geometrical things. So it's a beautiful, it's a very good thing. The disadvantages is that sooner or later, well, first of all, it applies to simple geometries. That is the first problem. So it's not going to apply to a conductor like that. Now, the second disadvantage is that you eventually get special functions, needs exponential functions, needs special functions. And you start getting into the Bessel, into the, I don't know, Legendre, and all sorts of crazy serious. The concept is very simple, but whenever you start using names that students have not heard in their lives, immediately think, oh, this is very high math, right? But today, Fayaz, how do you compute the log of 73.32 with a calculator? And if I ask you, compute the Bessel function of 73.32, what would you do?
I will look for some table or
You look for some tables or something.
or the
You just need the right calculator. The right calculator
yeah.
is called MATLAB. MATLAB has every function you can imagine. So, and just like sine of x, you will develop it as a zero, no, let's say cosine, which I know it better. Cosine of x, it will be 1, right?
X squared by 2.
Minus, no? It will be minus. Minus x squared by 2, blah, 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 blah. Okay. Just like that. And you calculators compute it like this. It's the same way you compute that and that. But a um, it's sometimes it's difficult to explain, sometimes it's difficult to understand because people are just don't want to get it. And of course, the other disadvantage is the price only for linear media. But they give you great insight, great physical insight. If you get to solve it, that will be good. It also gives you a how can I say? I would call it asymptotic um, insight, asymptotic behavior. It will also give you parametric variations, parametric studies. So therefore, these things are great for design. If you're going to design machines, if you're going to design whatever, this is the only way you have to do it, other than the scientific method of trial and error with finite elements. So you either have a closed form solution of an approximate problem, or you have trial and error of finite elements until you get it. That's it. Yeah. And I have seen the people who some of the people who worked a lot on this, like Sylvester, Chari, Lothar, all those people. They just had, for example, they have the induction machine optimizer, and what they do is they run 1,000 of solutions, and then they pick the optimum one. So, and that is a good way, but that's the brute force way. Now, the good thing is that also the other advantage of this is that it gives you um, to validate your numerical solutions, your numerical, in particular, FEM solutions. I will never believe any final element solution that a particular student gives me on arrival. On the solution they give me on arrival is wrong. So 100% sure it's wrong. But if it comes together with an analytical validation, say you want to you apply it to this crazy shape, and it gives you, and if you validate, and if you go and solve analytically, and you know, solve analytically means just go and find the right solution in the right book, because they are all solved, or most of the things are solved. by Smythe. They used to be, we used to say that if it's not in Smythe, the solution doesn't exist. That's simple. But over the years, people have been solving incrementally little more complicated things analytically. And now I can say there could be out there 5 to 10 solutions to different problems that are not in Smythe. But we used to say, it's not in Smythe, it cannot be solved. So if you're going to solve a problem with a conductor with that shaping here, I would say first solve the problem of a cylinder, validate it, and if your final elements gives you the same as your analytical solution, then I will believe it. Then you modify it, and I will believe that is correct. So analytical solutions are not to be completely neglected, but they need to be taken with a grain of salt, right? They are not going to give you the solution to the real problem, but they have a lot of value validating solutions that you are obtaining in a different way.
Even in the disadvantages, they have linear methods.
The linear media, so they don't apply to nonlinearities. So they don't apply to saturation. They don't apply to something that changes with the excitation.
The piecewise function that we define is also non. It's also the population functions can be defined.
If you do it piecewise, you are kind of solving it linearly, but then you need to solve it for every section.
Yeah.
Yeah. If you solve it for every section and combine it, it's all right.
It's called analytical.
You can do it, right? You can do it if you go that way, by piecewise, but you need to do it correctly. Yeah, because let's say in particular, when you're dealing with saturation, let's take only saturation, no hysteresis. That would be even worse. When you're dealing with saturation, and I'm going to do saturation like this in 3 sections, right? You need to be very, very careful, and I'm going to put it symmetrical over here. I don't know if I can do it exactly symmetrical, but let's say that is symmetrical. So you need to be very careful with this, whether if you are in the first linear section from between this point and this point, no problem, right? It's linear. Okay. But the moment you start going into the next section, say you go here and you go here. Now you need to decide whether in your problem do you actually need the value here, so the slope here, or you need the value that goes from the middle to from here to here. So do you need the average value or you need the incremental value? So this is average. And over here, the purple, here, this purple is incremental. Okay, so you need to know, am I going incrementally or do I want the big picture? Depends on which one you want is what you need to take. So piecewise linear, you go incremental, but don't make the mistake to think that you're solving the large view of the overall view of the problem when you really go in the middle of those things. So said so, it can be used, but you need to know what is what you need and what is what you are using. All right. All right. Transforms. As I said, transforms really what they do is, and it's just to solve the problem. Let's take advantages of transforms. Advantage of transforms is that they reduce the dimension by one order. So if you have a 2D problem, whether it is a function of x and y or a function of x and t, we will call it, both of them will be 2D. One is, of course, time, and the other is y. But from the point of view of math, we don't care, right? It's just a different variable. Xy is not different from xt from the point of view of the number of dimensions that you need to solve. Sometimes for some problems, the t is only taking the derivative on a first derivative, and then it was okay. So they reduced the dimension by one. However, transforms only apply to linear problems.
So the mappings are also transforms.
Conformal mapping. I don't think it's exactly a transform.
It also reduces the.
But it also, well, conformal mapping does the same, but I would say conformal mapping, I see it more like an incremental deformation, more like a deformation problem, more than a transform. That's the way I see it. But I can see I can see which way the way you're going, right? It's where is conformal mapping fits in all these things, right? I would put conformal mapping in the physical solutions column. Conformal mapping gives you, if you understand the physics, you could actually do it. Yeah. Well, that's the way people did it. Since machines started in the late 1900s to when before computers were powerful enough, I would say by the 1960s, 70s, many people were still doing conformal mapping because otherwise they couldn't solve the problem. And you see engineers of that time were very good at designing the shoes of the shoe of the polar poles for synchronous generators. Yeah. So, and they were doing all this with conformal mapping, which means pencil and eraser. Yeah. Just the drawing. Yeah. Okay. So, other problems that you need to for transform is the need to compute the inverse. The inverse transform. So you're trying to do something analytical, and now you cannot compute in general, you can't compute the inverse transform or something. If your solution happens to exist in the table of Laplace transforms and Fourier transforms, and you can get the inverse directly, good. If not, you're going to have to develop it in fractions, or you're going to have to develop it in something and recognize the terms and blah, blah, blah. And by when you finish, the whole thing is being already a mess. And if you want to try to explain it to your students, all your students are just going to, if you show it on class 2, before class 2, they would just give up. Say, I don't want to. And those are the things that make electromagnetic fields obscure. When people want to go analytically and transforms and those things, forget it. Forget it. No, we don't need to. It's a lot easier to understand final elements, as you will see, or maybe today or next class. Final elements is a lot easier to understand than this crazy mathematical solutions. For final elements, you only need to understand optimization. That's it. You need to understand the area, how to compute the area of a triangle in any shape and any form you have it, and optimization, least squares optimization, not even complicated methods of optimization. Least squares and the area of a triangle, and that's it.
This is the convolution, how you see the convolution is a linear.
The convolution is linear. Convolution is linear. And yeah, no, we don't want to do integrals. In life, nobody wants to do analytical integrals. Nobody wants to compute an integral analytically. So, there are nice tools. So the advantages is that a 3D problem becomes a 2D problem, and a 2D problem becomes a 1D problem. And we have the FFT, which makes this thing a little easier. Yeah. And FFT, you get it from MATLAB. Now, you even if you have an FFT from MATLAB, you need to be very careful about putting the correct frequency or whatever discretization, and you also need to make sure that you have the so the correct discretization and the right computer, right? You know what you're doing. And the advantage of this is that you probably don't need, no need of special functions. Other disadvantage of here is, again, I mean, at the end, it's an analytical solution, so simple geometries. Now, what is the point of going to an analytical solution when you most times need to get these things numerically? So, if you end up with a formula, that is great, because in the formula you can see whatever you say. No, let's say electric field is a function of x and y, and the function is, I don't know, cos hyperbolic of some function, let's say delta x, and the sine normal of omega y or something like that, divided by whatever, right? X squared plus y squared. Say that's your solution. You can tell from here how this will vary with x or with y, right? You could say, oh, whenever the term on top becomes zero, it disappears, right? So it means the field will disappear periodically with x and y, right? So that gives you things. And also you see, oh, as you increase x and y, the field is smaller. Now, if you get an equation in which the field grows as you come back far, you know it's wrong. So you can, in here, you can say, at some point, the field doesn't matter, right? How far you will have to go, say, in here, how far would you have to be x squared plus y squared? How far does it need to be?
That's the problem.
Depends on the problem, but in general, if the next thing is not adding more than 1%, you forget it.
Yeah.
If it's not adding more than 5%, you may even forget it. If it is not, it's still adding more than 10%, you may still want to go a bit more, a bit further. Yeah. But you will say, when X and Y make the problem 100 times smaller, forget it. We don't care anymore. So this will give you a graphs. So you would say, oh, this thing goes like that, right? So you can see it. So these analytical solutions and transforms are great. Finite differences is, I think, the best you can do. You don't have access to a finite elements program. Finite differences are very simple to understand, right? You take the derivative of a function of f of x, say, you would say this is approximately equals, you just don't take the limit, to fx for delta x minus f of x divided by delta x. Right? That is the definition of a difference. which is a derivative, um, uh, and we will call this the forward difference. You, of course, have the ddx f of x, which is about f of x, f of x just by itself, minus f of x minus delta x over delta x, and this will be the backward difference. If you add the two, let's say take the average, say 1/2 of this and 1/2 of that, then you will get a ddx or f of x will be, you just need to add it, right? 2 times delta x, 2 times delta x, and over here it will be the one that cancels. The one that cancels is the negative here. This one will cancel, right? That one will cancel with this one. So you're gonna get f of x, let me put it in black. F of x plus delta x minus f of x minus delta x. And this will be called the central, which tends to be better, than the than any one of the others. But it smooths a little bit the changes, because if you have a change at some point, those the forward and backward may give you a little problem at the boundaries. So with this one, the central difference, you can do better. Now, what we really need is the second derivative, not the first derivative. As you see, we have always second derivatives of things, right? This is second derivative, second derivative, second derivative. So we need to take again a derivative for this, right? And the only thing we do is we define this thing, we'll define it as g of x is equals to that. And then we go again and take the forward. So just substitute these things by g, by g, by g, by g. And at the very end, the second derivative with respect to x, central difference of f of x will give you f of x plus delta x. I am not going to do it. I'm just going to write it here because I have my notes. Minus 2 times f of x plus f of x minus delta x divided by 2 times delta x. Okay, and these are the central differences. Now, the theory of a taking differentiations of or derivatives of this has gone extremely crazy. There are some methods, extremely good methods of higher order. You can take the derivative of whatever. There exists what is called smooth differentiators. And you can take derivatives of very high order. The problem with derivatives is if you take derivatives of functions, for example, if you take the derivative with respect to time of sine of omega t, this will give you omega cosine of omega t, right? And if you take the next derivative, it will give you the second derivative with respect of sine of omega t. It will give you the negative of omega squared sine of omega t. But as you see, this factor comes down and down and down, which means the derivative, the corresponding derivatives are growing in size. So you have a small, you have a small original function. Oops. And after two derivatives, this function might have grown to a very large function because it's been multiplied by a constant. And normally this constant, if let's say it's the frequency 2 pi f 377. So very quickly it's going to go exploiting to something that you have problems. So, but there are these smooth differentiators. They are now in MATLAB. So the newer versions of MATLAB have already these smooth differentiators. That the only thing they do is don't take more points and don't take the points continuous. So if you go into the space and you normally want to take the contiguous points, right? What you would normally do. So for this guy, you take that one, that one. Let me change this. So for that one, you take this, 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 and this. But if you want to do it better, instead of that, you go farther. You can go farther. And instead of taking that, you take more numbers and you may even skip some of them. Okay, so it's a whole theory of a finite differences. And if you're going to build your own program, I would recommend go with finite differences. Don't go with finite elements. Now, eventually, if you have this needs to be built problem specific. Um, so unless you develop a big CAD and things similar to the final elements, and then you are not a getting anything. Advantages is that you can probably program it yourself. The disadvantages is that you need to build the program. So say you can program it yourself, or here it would be most probably you have to program it yourself. It will be problem specific. But if you are working for a company where the bosses are very cheap, which is normally the case, all the bosses are always cheap. They don't want to spend the money, but they give you the time. Go for it. Go for your final difference thing, and you will get it done easily. Um, um, Another disadvantage will be that the matrices are very big. This is are big. Change it. Very big. And I'm gonna make it better. Very large. Advantage will be that the matrices are sparse. So you don't need to operate on the zeros. What I mean is you have, just like in any power system that you have the elements in the diagonal and maybe you have a few here. In finite differences, you can always have a band matrix. So finite differences, let's say this is your domain. So you go here, 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 over there. So the band of the matrix is going to be defined by this element and this n plus one node. So that's what the band of this band will have. N plus one, that will be the width of the band. But even the band is very sparse because the elements here, if you go with it a traditional thing, it's only attached to four elements. If you go with the smooth differentiation, it may be attached to more, but still, it will be in a matrix that is 10,000 by 10,000, there will be 7, 8 elements, non-zero per row. So the matrices are still things. So you can use techniques for the solution of sparse matrices. Let me see if I'm not missing any disadvantage. Okay, yes, advantages. It can apply to irregular geometries. Different, and it can work for nonlinear too. Nonlinear media. So if you can have a geometry like this crazy thing, doesn't have to be thing. It doesn't have to be a sphere or a rectangle or something. It can be completely general. You can solve it like that. And the only thing is that you have to program it. Okay. It could be very efficient. Could be. I'm not going to say it is. Could be. Could be very efficient. Definitely more efficient than finite elements. Um, so it works well even for holes. Okay, so if your geometry has a hole here, it will work well. So you just have to define these things properly. And if this is a void, it will do it well for that. I think the only other disadvantage is that you need to discretize the everything. You need to discretize the entire domain. And if you have an open domain, you need to go to infinity. There are techniques, there are things that we use, like, for example, ballooning. If we start growing the differences more and more and more in an exponential way, so that in the end, you get to infinity very quickly with an exponential. All right. The next one is integral equations. I don't know if I should continue with these descriptions, but I'm going to go faster. I'm going to go faster with these things because I want to get to the final elements. And so integral equations, what they are is that you concentrate on the sources. So the function is you only need, or we only need, not you, we only need the sources. So I give you an example. In finite elements or finite differences, if you have a cylinder which is carrying current, you need to discretize all the way to infinity. In a in finite differences or in integral equations, sorry, you only need to discretize the inner part. So I will discretize it like this, right? You go like that, and you only need to discretize the source. This is the source of the field, right? So that will give you a lot of efficiency. So the advantages is that it's very efficient because you only need to discretize the sources. Disadvantage, it applies only to linear. And the reason is because we discretize this cylinder into smaller cylinders, and then we know the solution of that. Of course, for a big cylinder, it doesn't matter. But if I had something like that, then it becomes important. So let me go do it the same here. So if I have a shape like this, which is missing a chunk of it, so I can simply just think about it, right? Each one of these filaments that I am putting here, the magnetic field of them is circles around it. So I can go discretize the whole thing. This is the idea, right? In the end, the people who go with this one is going to go and going to give you, oh, what is the green function of this and what is the integral of some funky names of integrations. Like, you remember the names? No. Homdel, Homdel integrals, and some very crazy things.
Cauchy.
What?
Cauchy.
Cauchy. So you have crazy names of integrals. All integrals in the end are a sum of things. But remember, the moment I tell you, you need an integral of Fresnel integral. Riemann integral, so whatever, immediately you start thinking, oh, this is high math. Forget it, right? I don't need these people in my life. They don't, it just complicate my life. It's like having a bad family member that you want to get away from, or a bad friend. So they give you physical insight in the end, but you cannot solve a nonlinear PDF. You cannot solve a nonlinear problem, and you need to deal with something that it cannot even give you the analytical solution. You need to always get it numerically. So, but it could be very efficient. So if you have a problem that is that you need to solve, this is applies very nicely to change of insulators. So you have this and that. So you only discretize this. You don't need to discretize the whole infinite because you're going to get the solution. Basically, you're going to pulverize the source, make it little things that you can solve, then put them together. And when you do this, superposition of the whole thing. That is the whole thing. So say you have this arrangement, a conductor, right, of this shape. You discretize it into cylinders, plots of cylinders. You know the solution of the cylinder, right? So you just add the solutions, right? So the people who solve this will tell you that I am crazy and that there is a lot more sophistication than that. To which I will tell them, sure, but you cannot solve anything that is nonlinear. And all my machines in power engineering saturate. Yeah, so that's the end of it. Yeah.
A question. Like for integral equations, usually you don't get like a single value that represents all your integration volume or area.
No, yes, you would get. You just add them all.
So is it like a good method for getting like energy and circuit parameters
For what problem?
in general, like as long as it's linear? Like if I want to get, let's say, like leakage inductance or self-inductance.
The advantage is whether or not you can discretize the source easily or not. So if your problem is very large and you have little pieces of sources here and there, that's the right way to solve it. For example, the typical is the electric field or magnetic field coming from a conductor, hanging from an insulator, right? You only need to discretize the source. But you need the field in a very large part. Final elements, you will have to discretize the whole thing. The matrix becomes very large. And then it becomes inefficient. So this is when you use it. It's linear, the problem needs to be linear, and the domain that you want to solve is much larger in comparison to the source. That is the applicability of this. And there are commercial programs that do this. So if you want to compute the electrostatic field of a complicated arrangement of transmission line conductors, and you want to design the field, how to design, let's say, the insulator, right? The insulator will go something like this, right? A chain of insulators will go like this. So what is the shape that you need to, right? What is the shape of this? How long this needs to be, how thick this needs to be. This is the ideal problem for integral equations. There are not only integral equations, there are, I think I don't have another one, yeah. Integral equations can be volume and surface. Surface will even go better. You don't even need to discretize the entire thing, just the surface of this. Yeah, so I am not going to get into much of this because I like what they do, but I need to be able to solve all the problems with the same thing. Yeah. If you have a problem-specific thing, just like finite differences, integral equations will be the best. If you have a linear problem in which it's never nonlinear and you just need to solve it again and again and again, this is absolutely the best because it's fast. Okay, now we get into finite elements. The advantages of finite elements, first of all, is general geometries. It's also nonlinear. Non-linear media, okay. How can I say? General geometries, nonlinear, okay. Okay with internal problems. Disadvantages, I think the greatest disadvantage is need to discretize the universe. Of course, we are not going to discretize the universe because we can't. But what's happening, Fallas? Nothing? You're asking for
Talking about so we need to pray.
you need to pray now?
No, maybe we were discussing the time that.
I see. I see. So discretize the universe. So you need to do the whole thing for an external problem. So it's great for internal problems. Great for internal problems. So if you have nearby boundaries, that's what you can do. That's the best for it. If not, you need to discretize the universe. Of course, people have learned to do things, right? Infinite boundaries. Exist the infinite boundaries. Infinite boundaries are, we haven't gone too much into the boundaries yet. Infinite boundaries is they give you a Neumann boundary that represents a Dirichlet boundary in the infinity. We will talk about that later. Another thing is that it needs pre and post processing. So basically, you need an entire CAD program. If you cannot do the whole thing by yourself, you need a CAD program. some of the final elements programs like console and ANSYS, it will take your AutoCAD drawing and just integrate it. You still need to define all the domains and all these things, but at least you don't need to draw it again. Now, my experience is that you need to convert it to the software, to the CAD of the program. If you really want to take advantage of all parametric studies and all these things that final elements programs have, the best thing is if you just draw it there. If you import it from AutoCAD, for example, you're going to be importing it again and again and again. And after 2-3 times of importing, you're fed up with this thing because it never imports exactly. There's always little things that you need to correct by hand. At least that's my experience. The programs are not yet so well connected. And when you use the program itself to build your geometries, you can do parametric analysis and studies very easily. You can, all these programs, in particular console and ANSYS, you can input functions and say, instead of having dimension of a square 5 by 5, you enter A and B and you define A and B. So you can change it easily. Advantages is can be fast, can be efficient, and I would say up to 2D problems. It can be slow for 3D problems, right, Fayas? It takes forever, even in the supercomputer, right? It takes forever. And sometimes it will not even fit. You would exploit it completely. So, so you can always, it can be very, let's say, very large. And that's why frequently you need to take advantage of the symmetry. So frequently we divide the problem into maybe 1/4 of the problem, and if we can, we do it a 1/8 of the problem. So if you have a big transformer, let's say like that, and it's symmetrical and whatever, you will at least try to cut it into 4, right, like that, and you may even try to cut it into 8 like this, and then get the solution. But then you don't have the entire picture, and people will not even believe you that is right. So, anyways, for that, you need to solve the problem, a reduced problem first, show that you are actually solving the right thing, and it's very easy to make a mistake. Okay, I think that's all what I want to say about the solution methods. And I want to take the rest of the time for the final elements, which is in the end what we wanted. Let me tear the page here, tear the page. Right. Move this guy up. I'm gonna put it right there. Okay. So any questions to this point? Because we're gonna completely change the topic. We're gonna go final elements all the way. Since this point to the rest of the time is gonna be final elements. No questions out in Mexico?
Well,
about-
only for time domain problems, I think this differential, the first method that you show, the differential, which is the
Finite
name?
differences?
Finite difference. It's the
Yes.
only one that can be used in time domain problems, right?
It can. You have to discretize the time too.
With final element, no.
Final
I
element can give you the time too.
But this, I remember that a console using for time domain, it uses differential which name I forget the name of in Spanish I know, but in English the up method that you show in the previous slides.
Previous slide in finite differences.
Finite differences, yeah.
Here it
I
is.
know that finite element methods, I mean, this console uses finite differences for the time domain changes.
Yes, yeah.
It's like that because something similar like to EMTP that we integrate in time.
Yeah,
So
if you need to go with time, you need to do something with it. And finite elements themselves don't
Don't use
discretize the time.
Mhm.
It doesn't discretize the time, it discretize the space. So you
Mhm.
still need to do something with the time when you have time domain. Um, um, yes, so you need to solve the transient. You will have to get an integration method for the transient, right?
Mhm.
So yeah, and I am not sure what console does, but you can use any of the existing um, integration methods to.
Mhm.
So you can use Euler, forward Euler, backward Euler, trapezoidal rule of integration on any of the Runge-Kutta methods. Yeah. Now I
Okay.
don't know which ones are programmed in console.
Okay. Thank
Yeah.
you.
All right. Okay. There are several formulations of finite elements, and the classic formulation. You go through variational calculus, and you go and get the book from Cherry and Sylvester. Cherry and Sylvester. I think is spelled incorrectly. How do we spell correctly Cherry? It's with an this is with an I. Cherry. Yeah. So those are the ones who wrote the book for final elements for electrical engineering. But if you go and read the book, it's going to give you the classic variational calculus, and it's going to start that you start by defining a functional, and it starts by getting the functional up out in. So I don't suggest for you to go this way.
Radiation and calculus, it's linear.
Is it function of a function? No, non-linear.
Oh, just win one parameter and we see other.
It is f of g of x.
Yeah.
Yeah, that's what it is, right?
So we change, we change a little bit in g of x to see the effect on f of x.
Correct. So the mathematics are obscure and, in my view, not even needed. The way all classic final elements books describe final elements is just to confuse the enemy, right? They want to confuse you because they start with the functional. Okay, define the functional. Define the functional. And that's how they start. All start with the same thing. Just define the functional. And it's a different functional for every type of problem. For Laplace equation, one function. For Poisson equation, another one. For the diffusion equation, another one. Forget it. There is no need. So even though it is rigorous and it is the mathematical correct way to do it, I would tell you, forget about this because you won't be able to explain it to anybody, even if you understand it. Okay. I'm talking about explaining it to students. It's just not possible. Students will just give up much earlier the moment you start just saying this thing. And there is no need because using the Galerkin approximation, which I will recommend the book by Sikorski. The book by Sikorski defines this thing. It makes it friendly. Let me put it this way. He makes it student friendly. Student friendly. So the only thing you need is least squares. I would probably, I'm guessing here is calculation of area. Calculation of areas. And least squares minimization, which bring you to energy minimization. If I were to put it this way, I am going to yeah.
What is Larkin? Why are we?
It's a name of a person.
Yeah, it's a person name. But
Yeah.
there are various methods now we are just dealing with Larkin, like this is Larkin projections, transformation, these kind of
This
things.
is based on optimization. Yeah. The only thing that you need to do to solve this thing is to know that everything in physics always go to the minimum energy. Right? So
Let's suppose we take a projection of some figure.
we don't need to go that way. The way we go is just least squares. The least square is all we need. And you will be able to build your matrices for final elements by only looking at the area.
Okay.
Yeah. You will see how easy it is. All this crazy math that other people want you to go, there is no need.
So we are only dealing with these three.
Only least squares,
Why?
because that's enough to solve the problem.
There are many.
What we want to do is to solve the problem easy, right? You don't want to solve the problem difficult. Yeah. So why would you go? Let's say that you want to go to across a mountain. Right? Why would you go and climb the mountain to the summit and then go down when there is already a highway that takes you on the side and takes you to the same place? Right? Why would you? Just because you want to do it the hard way? No. Right? What's
I
that?
think Galerkin, if he was a scientist, maybe he has some innovations in other fields. So he's
Oh, no,
referring
no,
to-
of course, and if you go
maybe he's
to
referring to some other area.
no, there are some other things. There's many things that are called Galarkin, and there's many other things that are called Euler. Euler was the most prolific mathematician you can imagine. I think he wrote, I think, 800 papers and books. So something like that. And almost everything can be done with some of the Euler methods. Yeah. So it was unbelievably prolific. So the way I'm going to go is I'm just going to formulate the final elements problem as a minimization using least squares. That's all, and you'll be able to understand it easily. You
Galerkin method.
well, you can even erase the name. Say, forget about Galarkin. There is no Galarkin. Okay. Optimization, through optimization, right? That's it, if you want to go that way, right? How things start. You see, I'm gonna delete this guy. Delete it. So we don't even know the name now. So there is no name for this. So no name, because the name seems to be sparkling some controversy here. So we delete the name of the person. Normally we like to give the name of a person, but to give them credit. But we decided that it's a funny name that we don't like because we don't want to explain it. Yeah. All right. So the whole thing starts with computing the area of a triangle. Why of a triangle? So it starts with the discretization of with the area of a triangle, because if you have a phonic shape like this, you cannot discretize this with only squares. So if you have square from here to here, and then the next square will have to go from here to here, and you're leaving an empty space, right? You are not considering just by that, you are wasting already this. Oops. So you are not considering that. And if you continue with the squares here, again, you're not considering this. But if I copy, paste, but if I go with triangles, so if I can have a triangle there, I can have a triangle here, triangle there, and I can continue with triangles all the way, almost regardless of which shape this has, because if I have a complicated region, I can just make the triangle smaller, right? So a triangle fits very well almost any shape. It's not perfect.
Necessary that we have a same
Yeah.
area.
Almost the same. We always make a little mistake because
Triangle
you cannot put something flat on something round, right? So you go like this, so it's not exact.
I'm talking about the area of triangle.
The-
It shouldn't be fixed.
No,
Okay,
no,
it
it can be any shape. The only thing of this method is that there needs to exist. The area needs to exist. So if you have a pointy thing like this, right? Or no, the classical method, say you have a duct, and inside the duct, you have a cable. And now you come here and zoom into this region, you're going to have a curve like this and a curve like that, right? And they are touching at a point. So inside here, you will have a degenerate triangle, right? You will have a triangle here, which is so small with so very little area that will give you problems. So degenerate triangles are not good.
Want them as equilateral as possible.
You want them, you don't want any degenerate triangle because we are going to divide by the area. So if the area is very small, we're going to magnify the errors a lot. And the matrix could come and tell you it's singular. I can't deal with it. Or it can take a lot of problems. Now, over the years, they have learned to deal with this. I have learned to deal with this very easily. I take the big external duct and come with the cable, make a linear here. So make the cable like this. Sorry. So make it like this, flat. And that is actually more physical than having, I'm going to use the word osculation. This is an osculatory thing. Osculatory. Osculatory is kiss. Okay, that's what it is. It's a kiss. So the two things are kissing each other at a point. Yeah. So, but that wouldn't happen. If this is a cable, it has some weight and it has materials that deform. So there will be a flat region at the bottom. It will not be a perfect, it will not be the contact in a single point. So make it like that. And then your triangles have no problem, right? On both sides. Yeah. Other people deal differently. They deal with different types of elements. But so this is the way that I solve these things, not too much of a problem. Okay. Said so, let's compute the area of a triangle. The area of a triangle, I'm gonna put it in the XY coordinates, and the triangle is going to be any triangle. The one I draw is this one. Just one triangle. And this is going to be 0.3, P3 of coordinates X3, Y3. That's it. This is going to be, I'm going to call it vertex 3, vertex 2, which is going to be a function, or its coordinates x2, y2, and this is, of course, vertex 1, which is x1, y1. The area of a triangle is base times height divided by 2, right? And I can take any one of these things as the base. So, because it's my class, I am going to take the base. This is going to be the base. Let me put it in red. This side is going to be the base. Okay, and the height, of course, is going to be that one. It has to be, because once that I select the base, I have I am not free to select the height. So what is the length of the base? The length of the base will be the distance between vertex 2 and vertex 1. So it will be x2 minus x1 squared, square root. Plus y2 minus y1 squared. Okay, that's V. Now, I need to get a perpendicular. I need to get two things. This point, right? The point there, at what point this H comes out, and the equation of the line that is perpendicular to this one. So for that, I need to compute the slope of M. What is the slope? The slope of the line here, the slope of this line, right? Of this of line B.
Yeah, the slope of the line is the inverse of slope of H.
Okay, that's in the end. In the end, yeah, exactly. So I want MA. And in the end, what I want is MA over MB over MH, right? I want, this is MB, the slope of V. Slope of V. In the end, I want that the slope of V times the slope of H to minus, right? So what is the slope of B? It would be y2 minus y1, x2 minus x1. That's the slope. Right? So therefore, MH, the slope of MH is equals to the inverse of this, x2, when there's a negative here, there's a negative there, x2 minus x1, y2 minus y1, therefore is going to be x1 minus x2 divided by y2 minus y1, right? Unless there is a problem or something, right? And so now I need to find the intersection. Okay, how do we find the intersection? Intersection, let's call it a point C. And this will be point C. Who knows trigonometry? How do you find the intersection between, you know this other thing. Well, I have already computed it. I am not going to go through the whole derivation. So, but I have already computed that h is equals to this equation. H is equals to the absolute value of x2 minus x1, y1 minus y3, minus x1 minus x3, y2 minus y1, absolute, and divided by the square root of x2 minus x1 square plus y2 minus y1 square. Of course, this is v, right? This is v. What's that? I don't have the intersection. I just computed this thing. I copied it from a book, right? Yeah.
What, this is to calculate the area, right?
We haven't computed the area. At this point, I only have
Yeah,
h.
yeah, but it is for calculating the area.
Exactly.
So my question, why don't we go to cross product?
You could. No problem, you could. But you still have you still need the equation of the two vectors.
Uh-huh.
So it's in the end, it's exactly the same thing. Yeah. Yeah, no problem. The only thing is you need the area. So the area then is going to be 1/2 of B times A times B, right? A times H. Sorry, B times H. So the area is 1/2 of the absolute value of x2 minus x1 that multiplies y1 minus y3 minus x1 minus x3 times y2 minus y1. Absolute value. All right. Let me see. This has to be, it looks ugly. This is x3. Okay.
Connector product, it is also about.
Yeah, it's the same thing. Yes,
Same
yeah. Yeah. Simple trigonometry from high school, right? But you need to do a page of derivation because now you need to get the intersection of two lines, two slopes, two things, right? So, but you understand that it's possible in the, I don't want to go through the whole details, but of course, this class has no homework, but homework. Homework. Convince yourself that A is correct. We're going to use the area for everything. The only other concept that is important is when we have a big thing, and we discretize it in triangles, right? So we have I am putting big triangles because that's what I am doing this point. So we are going to solve the problem of finite elements. We're going to solve it for the vertices. Yeah. So what happens in the middle? So we need to have a solution for a point of interest that is here, right? Right in the middle, inside the triangle. So for that, finite elements does what is called a linear interpolation. So the value of a function in a linear, and it's exactly as you would do, for example, let's say that this is x and this is y. And you have the values at 2 points, right? You have the values of x1, the value of x2, which is, will correspond to y1 and y2. And you want to interpolate in between, right? So you want to interpolate into the point xi, yi. Right? Of course, this is xi. I is for the interesting point, right? So this is point A. This is point 1. This is point 2. Okay, so how do you interpolate? Well, you get the equation, right? You get a you compute the slope. The slope is going to be y2 minus y1. We already have it, x2 minus x1. And you compute a v. You need to compute the intersection here, b. I don't want to confuse it with that b over here. It's not, this is b from the equation y equals to mx plus b. Different from that b over there. So this b here is not this one here. Not the same b, but this is the intercept, right? This is the intercept. The intercept, and this one is the length of the base. Okay. Okay, linear interpolation. Well, you just have to compute the equation, right? You compute the equation there, blah, blah, blah. And then to get, you know, it's the same equation. You just evaluate. Once that you get V, you just need to, once that you compute the slope, you just need to evaluate for x equals 0, and that's it, right? Then you do the linear interpolation, which will be yi will be m, whatever you have, xi plus b. And with this equation, you can compute the value of y at any point there. Now, for a triangle, let me put the same triangle. Let me copy the same triangle. Yeah, but I don't want to, all these things, I don't want it. No. Copy. Okay. I don't need this. I don't need this. But the other things I do need. Let's say that I want to find the value at this point of coordinates xi, yi. So this, we are getting into the dirty little details of finite elements. It's only geometry, but it is very important. So, assumptions. I am willing to repeat this part next class if it is not clear, but this is the central part of finite elements. Assumptions is we know B1, B2, okay. Something is not going correctly here. I cannot erase. We run out of charge. No, it's something different. It got stuck. So I need to close and reopen. I don't lose any changes, don't worry. So I think maybe it'll come now and I don't have anything, right? No. No, as I see, nothing has been lost. So let's see if this still works. V1, V2, no. No, something is not right. Let me see here. This is okay. So let me go to my office and get the other one.
पर आप नहीं आएंगे मुझे पता है नहीं। आज 3 बजे क्लास खत्म नहीं होगी। खत्म हो गई। 3:30 नमाज पढ़ जाओ। हाँ जी।
Okay. So now let me see. This one works. Okay. But it doesn't erase. So technology is not, is failing me now. So V2, now it's only erasing. We know we know the values. We know not this thing. We know the values of the function at we know the values. This is not good. Yeah, let's change the batteries. So technology is failing me. This one. Okay. I think I got it. Let me put this back together. We know the values of the function at V1, V2, V3. And that's, of course, something that we're going to compute from the final elements process. But to get there, we're going to define something that I call the shape functions that start with an interpolation of this. So the way we interpolate here, we say the value of the function of the value of the function of at x1. Let me see if it erases. Yeah. The value of the function of b of x1, y1, which is equals to v1, will be equals to ax1 plus by1 plus c1. The interpolation function is v of x and y equals to a of x plus b of y plus c. This is the function that I am going to, which the function that I am going to interpolate inside the triangle. So I'm going to say inside the triangle, any value here inside the triangle is going to be given in this way. And it will come from the known values at this point, and this point. All right? So the voltage at x2, y2, which is equals to v2, will be just the same, ax2 plus by2 plus c2. And the value of x3, y3 will be v3 equals to ax3 plus by3 plus c3. All right. And out of this, these are known. They are not known yet, but they will be known in a moment, right? They are, in the end, this is what we want to compute. Out of the finite elements. Finite elements is all about computing the value of the functions at the nodes. But we are going to assume for now that we know them so that we can do the interpolation inside the triangle. At some point, we will compute these values A, V, and Z, and then we will know it. Yeah, because we know the coordinates. So what we really don't know here is A, B, and C, right? All right. So with this, we can write a matrix that has x1, y1, and 1, and here we'll be multiplying A, B, C. A, B, C, and it will be x2, y2, 1, x3, y3, 1. And value v1, value v2, value v3. Of course, it's v1 of x1, y1, value of x2, y2, and value at given at x3, y3. All right. What's the time? Huh? 10 minutes. Okay. All right. So now we need to little trick here. A trick, but is mathematically accurate. Say that we want to solve for the voltage at any point. The voltage of the value of the function of x and y. So which will be given of ax plus by plus c. And I need to derive it. I can prove that this is equals to 2 times the area the sum from I equals 1 to 3 of xy. No. I think I'm going to stop here and I'm going to do this correctly next time. What I want is to write an equation that goes like this. This is the final answer. V of x and y is going to be given by 1 of 2 times a, but I need to solve this equation. I need to solve these equations analytically. Yeah. So I need to solve this equation. And I am going to show, I can do that in advance. Let me do this. To solve this equation, I need to compute A, B, C. I need to compute the inverse of this matrix. Let me call it matrix K. Matrix K, right? I need to compute the inverse of matrix K, and it will be the values B1, B2, B3. Let's start by computing the determinant of matrix K. To compute the determinant of matrix K, I take the easiest way, it will be if I go with these ones, right? I take that one and get the product of this times this. So it would be x2 times y3 minus y2x3. Okay, so that is the first product. Then I go with the negative of the next one, right? Now I get the other one, which is going to be this guy is going to take that and that minus that and that. So it's x1, y3, x1, y3 minus y1, x3. And I take the next one, minus, no minus, it's plus. Plus the next one, which will be the top two parts here. So it will be x1, y2 minus y2, x3. All right. Now let's do, some of these things are going to eliminate. So so this determinant, I'm just gonna forget about the matrix. So let's see which elements eliminate here. X2, Y3, I don't have it. Y2, X3. So let me reorder X2, Y3. I'm gonna put the X first. You have the answer? Yes, yeah, but I want to derive it. I want to derive it, yes. So it's going to be x2, y3 minus x3, y2 minus x1, y3 minus plus x3, y1 plus x1, y2 plus y2, x3. Okay. Anything eliminates? No, here. Oh, yeah, but this one I put it wrong. This should be x3, y2. And that one eliminates with this one and this one. Yeah. You don't like it. I just put, to be able to see it, I put the X at the beginning, right? So This is x2, y3. This I just change it, x3, y2. Negative x1, y3. Positive x3, y.
That one is negative.
Nothing cancels out.
Oh. It has to cancel. So then probably then I made a mistake on this in this thing. So let me do it again. If I take the first one is x2, y3, x2, y3 minus x3, y2 minus x3, y2. Then the next one is a negative, right? I took take the negative of this, so it's going to be x1, y3 negative, x1, y3 negative, and then it's going to be x3, y1 positive, x3, y1 positive. Then the last one is going to give me positive x1, y2 and negative y2, x3, which should be negative. Right? This one has to be negative or is negative. Negative there. Yeah.
The middle terms cancel. Oh, no.
Yes.
It's x1, x2.
Yeah, no, you're wrong. Yeah, nothing cancels.
Okay. We stop there because it has to cancel. So we're gonna stop here because this needs to cancel. So one of these needs to cancel, and in the end, the determinant needs to be 1/2 of the 1/2 area, like this. This is what I'm looking for. The determinant is that. Okay. But there's nothing is canceling here. Do I have a problem here? No, x1, x2, y2, x2.
Doesn't it cancel if you don't go through the ones column, when you do go to x1, y1, 1?
But the determinant needs to be the same.
Yeah.
We leave it here. I'll fix it for next time. In any case, it's already late. All right. I'll fix it for next time. Any questions?
No.
Fermin?
No, doctor.
Yeah. All right.
Yeah.
So see you next time. Let
See
me
you. Thank you. Bye.
put the video.
See you next week. Thank you.
All right. Bye-bye.